Good day, my beloved apprentices, and welcome to the final week of electrochemistry. Previously, we have investigated the galvanic cell. Now, we will look at the electrolytic cell. We will start with our study of the electrolytic cell by looking at the electrolysis process. Electrolysis is a process where electrical energy is used to start a non-spontaneous redox reaction. Why non-spontaneous? Remember that a spontaneous reaction will occur naturally under a given condition. A non-spontaneous reaction, however, will not occur under a given condition. Thus, electrical energy is needed to start the reaction. After all, why would you need energy to start a spontaneous reaction? It will happen anyway. An electrolytic cell is a type of electrochemical cell where electrolysis happens. The redox reaction that occur at the anode and cathode of an electrolytic cell will form products that can be collected. To study the process, we can either look at the products formed at each electrode, or we can determine the amount of product formed at each electrode. However, before we go there, let us look at the components of an electrolytic cell. In an electrolytic cell, we have an electrolyte, which is a liquid or solution that contains free-moving ions, two electrodes, anode and cathode, that are partially immersed in the electrolyte, and a direct current electrical power supply that will provide electrons to the cell. Remember, reduction occurs at the cathode. The electrons for this process is supplied from the negative terminal of the power supply. Oxidation occurs at the anode. The electrons released from this process flow to the positive terminal of the power supply and completes the circuit. Let us start at the negative terminal of the electrical power source. Electrons flow to the cathode, which will become negatively charged. Positive ions or cations in the electrolyte will be attracted to the cathode. At the cathode, these cations will be discharged or loses its charge by accepting the electrons. The oxidation number of the cation will be reduced. Thus, reduction occurs at the cathode. The anode, which is connected to the positive terminal of the power source, is positively charged. This attracts negative ions or anions in the electrolyte. At the anode, the anions will be discharged by releasing electrons. The oxidation number of the anion will be increased. Thus, oxidation occurs at the anode. Electrons flow through the wire or external circuit, while free-moving ions move within the electrolyte. This completes the electrical circuit. All cations in the electrolyte will be attracted to the cathode. All anions in the electrolyte will be attracted to the anode. However, only one ion will be discharged at each electrode. This will not be a problem if there is only one cation and one anion in the electrolyte. But if there is more than one anion and cation, only one of each will be discharged. The ions that will be discharged will determine the products formed at each electrode. There are three factors that determine which ions will be discharged at each electrode: the standard reduction potential of the ions, the concentration of the ions, and the type of electrode used in the electrolytic cell. Let us now look at the first factor that will determine the ions to be discharged in an electrolytic cell, which is the effect of the standard reduction potential. The ions that are present in an electrolyte depend on the type of electrolyte. Molten substances, usually liquid ionic compounds at very high temperature, contains ions in the liquid phase. Pure water hardly contains any ions due to the low value of its Kw. Usually, a little bit of acid is added to allow water to dissociate more and produces hydrogen cation and hydroxide anion. Aqueous solutions contains hydrogen and hydroxide ions from the solvent and cation and anion from the solute. Let us now investigate these three types of electrolytes. Molten electrolytes are usually ionic compounds in liquid phase. This means that the solid ionic compound must be melted at high temperature. Once melted, the ions are free to move around. For example, molten sodium chloride has only one cation, sodium ion, and one anion, chloride ion. At the anode, chloride ions will be oxidized to form chlorine gas by releasing electrons. At the cathode, sodium ions will be reduced to form sodium metal by accepting electrons. Before adding up the two half reactions at the anode and cathode, we must ensure that the number of electrons exchanged between these two electrodes are equal. In this example, the cathode half reaction is multiplied by 2. Please be aware that the multiplication factor shown in red in this slide must not be written when you are asked to write the cathode or anode half reaction equation. A balanced chemical equation must always show all relevant chemicals in the smallest mole ratio. The overall balance equation can then be obtained. Let us look at an electrolytic cell that uses molten sodium chloride as the electrolyte. Electrons from the negative terminal of the power source causes the cathode to be negatively charged. This attracts the sodium cation in the electrolyte. Sodium ions are discharged by accepting electrons and are reduced to sodium metal. Since liquid sodium metal is less dense than molten sodium chloride, the sodium metal will float to the surface of the electrolyte. Chloride ions in the electrolyte are attracted to the positively charged anode. Chloride anions are then discharged by releasing electrons and are oxidized to form chlorine gas. The gas can be collected from the top of the anode. Here is another example involving molten potassium bromide electrolyte. You may pause this video to look through this example. Now, how about pure water? Let's just say it is one useless electrolyte. Recall what you have learned in LU5 about the water dissociation constant, Kw. The value at room temperature is just 1 times 10 to the power of negative 14. That means there is a very small amount of hydrogen ion and hydroxide ions in pure water. The amount of products formed from the discharge of these ions are also very small. We can say it is negligible. In fact, we can say that since there are almost no products formed, pure water cannot be electrolyzed. However, by adding a bit of hydrochloric acid into pure water, the dissociation of water will increase. This increases the amount of hydrogen ion and hydroxide ion in water. Hence, there will be enough products formed at the electrodes. Take special note at how hydroxide ions are discharged at the anode. You will be wise to remember this half reaction, as this is a very common redox reaction. If you have done this experiment in school, you probably remember that oxygen gas are formed at the anode and hydrogen gas are formed at the cathode at a ratio of 1 to 2. Now, what if we have an ionic compound such as sodium chloride and dissolves it in water? We will have a sodium chloride aqueous solution. Like molten sodium chloride, aqueous sodium chloride also have free-moving sodium ion and chloride ion. Additionally, there are ions from the solvent, hydrogen ion and hydroxide ion. The discharge half reactions for each of the ions are as shown. However, only one cation will be discharged at the cathode and only one anion will be discharged at the anode. So, which ions will be selected at each electrode? Now is the time to once again summon the big mama of all electrochemistry table, the standard reduction potential table. To determine which ion will be discharged at the electrodes, we just need to compare the standard reduction potential or E0 values of the cations and anions. Since reduction occurs at the cathode, the cation with the higher E0 value will be discharged there. Since oxidation occurs at the anode, the anion with the lower E0 value will be discharged there. And that, kids, is how your old electrochemical series was constructed. Note that to make it easier for our comparison, we only compare a cation with other cations and an anion with other anions. As an example, if there are zinc ion and hydrogen ions in the electrolyte, the hydrogen ions will be discharged. Hydrogen gas will be formed at the cathode. If there are hydroxide and chloride ions in the electrolyte, the hydroxide ion will be discharged. Oxygen gas will be formed at the anode. Take note that some ions will not be discharged at all, such as nitrate, sulfate, and fluoride ions. There will be no product formed at the anode for these ions. Now I leave you with this exercise. Please pause this video as you attempt the exercise. Once you are ready, press play to continue. Ready? Here are the answers. Both magnesium ion and hydrogen ions are attracted to the cathode. However, due to the higher E0 value of hydrogen ion, as seen in the standard reduction potential table, hydrogen ion will be discharged by receiving electrons. Hydrogen gas will be formed at the cathode. Both nitrate and hydroxide ions are attracted to the anode. However, due to the lower E0 value of hydroxide, as seen in the standard reduction potential table, hydroxide ions will be discharged by releasing electrons. Oxygen gas will be formed at the anode. Naturally, you may also use the electrochemical series that you probably remember more than your childhood to determine the ions to be discharged. By combining the two half reactions, we will get the overall electrolysis equation as shown. Let us now look at the second factor that will determine which ions will be discharged at the electrodes. This second factor is easy because it only applies to anions. Anion, which is present at high concentration, tends to be discharged at the anode, regardless of its E0 value. Consider the electrolysis of concentrated magnesium chloride solution. Both magnesium ion and hydrogen ions are attracted to the cathode. However, due to the higher E0 value of hydrogen ion, as seen in the standard reduction potential table, hydrogen ion will be discharged by receiving electrons. Hydrogen gas will be formed at the cathode. It is a different story at the anode though, where the second factor comes into play. Even though hydroxide should be discharged due to its position in the electrochemical series, chloride ion is discharged instead. The high concentration of chloride ions in concentrated magnesium chloride is the reason behind this. Chlorine gas will be produced at the anode. The overall electrolysis equation is as shown. Finally, let us look at the last factor that will determine the ions to be discharged at the electrodes. You have probably noticed that all the earlier examples and exercises made use of inert electrodes. Inert electrodes do not react during electrolysis. Examples of inert electrodes are graphite and platinum. What if a metal electrode is used instead? Noble metals such as platinum are inert. However, other metals tend to be reduced and oxidized, depending on their E0 values. These metals are active electrodes. Let us look at the electrolysis of copper sulfate solution using copper as electrodes. Both copper ion and hydrogen ions are attracted to the copper cathode. Since copper has a higher E0 value than hydrogen ion in the standard reduction potential table, copper 2 ion will be reduced to copper metal. The copper metal will deposit around the copper cathode, making the cathode thicker. Both sulfate and hydroxide ions are attracted to the copper anode. Hydroxide is supposed to be discharged at the anode. However, due to the higher tendency of copper to be oxidized compared to hydroxide ion, the copper anode itself will be oxidized to form copper 2 ions. This causes the copper anode to become thinner. The copper ions formed will enter the electrolyte. The blue color of the copper sulfate solution is caused by the presence of copper 2 ions. Since the amount of copper ions discharged at the cathode is balanced by the amount of copper ions formed at the anode, the intensity of the blue color solution remains unchanged. To recap, the three factors that will determine the ions to be discharged at the anode or cathodes are the standard reduction potential of the ions, the concentration of the electrolyte, which only affects the anion, and the type of electrodes, whether inert or active. As you have learned in the first lecture, the electrolysis process that occurs in an electrolytic cell is the reverse of the process that occurs in a galvanic cell. A galvanic cell is used to provide electrical energy. What then are the uses of electrolysis? Industrial uses of electrolysis includes the extraction of metal from its ore, the anodization of aluminium, the treatment of effluent, electroplating, and also in the manufacturing of chlorine. We will investigate these 5 applications separately. Aluminium is a very useful metal. Just look around you. The can of drinks you have bought from the vending machine is made of aluminium. Some of your smartphone casings are made up of aluminium too. Okay, let's get one thing out of the way. How exactly do we spell aluminium? Is it aluminum or is it aluminium? Both are correct. Aluminium is the British spelling, while aluminum is the American spelling. But since we are in Sarawak, we'll call it aluminum ja. Sorry, I apologize. I'll show myself the door. Aluminium is a rather reactive metal. Due to this, it does not occur naturally as pure metal. Aluminium typically forms compounds with other elements such as oxygen and silicon. This compound in the form of ores are known as bauxite. Once mined, bauxite is purified to aluminium oxide or alumina through the Bayer process. Aluminium oxide is then melted to form the electrolyte for an electrolytic cell called the Hall-Héroult cell. Since the melting point of aluminium oxide is rather high, cryolite or sodium hexafluoroaluminate is added into it to lower the melting point to about 980 degrees Celsius. Let us now look at the Hall-Héroult cell. This industrial electrolytic cell is made up of carbon anodes immersed in the molten mixture of aluminium oxide and cryolite. The outer case of the cell is the cathode. The anodes and cathodes are connected to the power supply. An opening at the bottom of the cell allows liquid aluminium to be extracted as it is formed, since liquid aluminium is denser than the electrolyte mixture. How then can pure aluminium be extracted from the electrolyte? The two cations, aluminium ion from molten aluminium oxide and sodium ion from cryolite, are attracted to the cathode. Aluminium ions will be discharged due to its higher standard reduction potential or E0 value compared to the sodium ion. The aluminium produced is also in the liquid state due to the high temperature of the Hall-Héroult cell. The oxide ion from aluminium oxide and the hexafluoroaluminate ion from cryolite are both attracted to the carbon anodes. Due to its lower standard reduction potential compared to the hexafluoroaluminate ion, the oxide ion will be discharged to form oxygen gas. The half reactions at both the anode and cathode can be written as shown. Before we can add these two half reactions to obtain the overall equation, we must ensure that the number of electrons in both half reactions are equal. To achieve this, the oxidation reaction is multiplied by 3 and the reduction reaction is multiplied by 4. The 12 electrons in both half cell reaction can now be cancelled to obtain the overall equation. Once again, you do not have to write the multiplication factors shown in blue and red when you are asked to write the half reaction equations for each electrode. Liquid aluminium is then extracted from the bottom of the cell. Typically, oxygen gas produced at the carbon anodes will just diffuse away. However, since the Hall-Héroult cell is operating at a very high temperature, the oxygen produced will react with the carbon anodes to produce carbon dioxide. This will corrode the carbon anodes, eventually making it too thin to function. Thus, the carbon anodes must be replaced regularly to ensure continuous operation of the cell. Let's look at another application of electrolysis, which is also related to aluminium. The electrolysis process involved is known as anodization. Anodization is a process whereby the surface of a metal, such as aluminium, is thickened with a layer of its natural oxide. What is the use of this process then? Some metal oxide layer is rather tough and provide a strong protective surface for the metal. This will make the metal more resistant to corrosion and wear. Now, some metal like iron are not suitable for anodization. When iron oxide covers the surface of iron, it will not be of much use since iron oxide or rust is very brittle. Aluminium oxide, however, forms a tough layer that can protect aluminium. The oxide layer from the anodization process are usually porous. This enables substance such as paint and glue to attach more strongly to its surface. The photo shows several products that have anodized surface. I'm sorry if you cannot recognize these Stone Age relics. The devices on the right are iPods, portable music players popular during the Brooke era. The setup below shows a simple electrolytic cell for the anodization of aluminium. The metal to be anodized will become the anode. Lead is used as the cathode, and the electrolyte used is dilute sulfuric acid. Hydrogen ion from the electrolyte is attracted to the lead cathode and undergoes reduction by receiving electrons from the power supply. Hydrogen ions are reduced to form hydrogen gas. The hydroxide ions are attracted to the aluminium anode and undergoes oxidation by releasing electrons, which returns to the power supply. Normally, the oxygen gas form will simply diffuse to the atmosphere. However, since aluminium is a reactive metal, it will react with the oxygen gas produced to form aluminium oxide. This tough aluminium oxide deposit will form a thin layer around aluminium. This is the anodization process. These are the half reactions that occur at the cathode and anode. What is important here is the formation of aluminium oxide layer that surrounds and protects the aluminium anode. The third use of electrolysis that we are going to explore is in the treatment of effluent. Effluent are industrial waste that are discharged into open waters such as rivers, lakes, or the sea. This waste from industrial processes often contains harmful chemicals that must be removed. Some of these harmful chemicals include heavy metals in the form of ions, such as cadmium ion, chromium ion, and nickel ion. Why are these metal ions harmful? They can cause heavy metal poisoning if ingested by living organisms such as us. In 1912, during the final years of the Meiji era in Japan, and manga was just a fruit, I'm so sorry for this lameness, a cadmium poisoning incident occurred in the Toyama prefecture in Japan. Effluent from mining industries that contain cadmium ions are found in rivers in the prefecture. These rivers are the sources of water for the locals, including as drinking water. The cadmium poisoning was also called the Itai disease, which means painful. This poisoning leads to the weakening of bones, anemia, and kidney failure, which have ended up in death. It is important then to learn from history. Electrolysis of effluent can be done to remove the heavy metal ions from the effluent before it is being released to open water. Metal ions are water soluble and cannot be easily removed from the effluent. During electrolysis, metal ions are reduced to solid metal, which can be easily filtered from the effluent. Take a look at those shiny car bumpers, earrings, and Milofast spoons. Chances are that those items have gone through electroplating. Electroplating is a process where a metal coat is applied to the surface of other metals. This is typically done to provide a protective coating to the metal items or to thicken metal components. According to Dana's law of electroplating, an observation made by one of the most brilliant minds in the multiverses, women love to bling-blingize themselves, while men tend to bling-blingize others. This may sound sexist, but tell me, have you ever seen men decorate themselves with earrings for fun? You have? Then those are not real men. They do not obey Dana's law. Disclaimer, this is just for fun. I wear 2 rings, so... Let's look at how you can coat your normal dull spoon with a layer of shiny silver to impress your potential in-laws. First, you would need to borrow a beaker from your chemistry lab, wires with alligator clips, silver nitrate solution, and a bar of silver. Unfortunately, we don't have silver in our lab, so you'd have to get it from your parents' jewelry collection. You can buy some batteries, and you already have the dull stainless steel spoon. To electroplate the spoon, make sure that it becomes the cathode by attaching it to the negative terminal of the battery. The silver bar is the anode attached to the positive terminal of the battery. At the anode, silver undergoes oxidation by releasing electrons to become silver ions, which will flow into the silver nitrate solution. These silver cations are naturally attracted to the spoon cathode. Over time, the silver anode will become thinner as more and more silver are oxidized to ions. At the cathode side, the silver ions in the solution receive electrons and undergoes reduction to form silver metal. This silver metal will form a thin layer around the spoon. Take note, however, only the part of the spoon that is immersed in the solution will have this silver coating. Here is another example where your normal safety pin is electroplated with copper. Please pause this video and study the half reactions at the anode and cathode. Once again, notice that the item to be electroplated must become the cathode, while the metal used to form the coating must become the anode. Finally, we will look at the last application of electrolysis in your syllabus. So, why do we need to manufacture chlorine? Chlorine is a diatomic molecule that exists as a yellowish-green gas. It is obviously toxic to us. It does have many important uses. One of the uses of chlorine is in the manufacturing of organic compounds that can be used to produce polyvinyl chloride, or PVC. This is the substance used to make pipes, cables, and clothes. In this electrolytic cell, graphite is used as the anode and mercury is used as the cathode. Brine, which contains sodium chloride, is used as the electrolyte. At the cathode, sodium ion in brine will be reduced to sodium metal. This metal combines with the mercury cathode to form a sodium amalgam, which can be removed. Mercury is then recovered from the removed amalgam. At the anode, the chloride ions in brine will be oxidized to form chlorine gas. The chlorine gas is collected from an opening at the top of the electrolytic cell. Alright, we have just looked at 5 uses of electrolysis process. In the next lecture, our last lecture, we will delve into some calculations to determine exactly how much products are formed at the electrodes of an electrolytic cell by using Faraday's law. See you then.